In example 3, we're going to look at a different type of function, one that mixes polynomials and exponential functions. We are going to sketch the curve using the first and second derivatives of c of x equals x squared times e to the x power. So there is my function. It should be clear that the domain of this function is all real numbers. There's no way I can divide by 0, and there's nothing that I cannot put inside the exponent of e. I can put negative numbers, positive numbers, 0 into this exponent and just be fine. And then any real number I can square. So as long as I can square any real number, put any value in an exponent, I'm good to go. So the domain is all real numbers. That means I'm going to start looking for critical values. In order to look for critical values, I need to find the first derivative. The first derivative is going to be calculated with doing a product rule. We take the derivative of the first component plus normal second component, or excuse me, times normal second component, plus normal first component times the derivative of the second component. Hopefully you remember the derivative of e to the x is e to the x. That's what we get. I like to look at this first derivative a little bit differently. I would rather factor out that e to the x and say my first derivative is x squared plus 2x multiplied times e to the x. I think that's easier to see. So my original function was polynomial times e to the x, and my derivative now is polynomial times e to the x. If I want to look at critical values, I set that first derivative equal to 0. Once again, I'm setting that equal to 0 because there's no way in which this can't exist. The domain of the derivative is all real numbers. If my first derivative is set equal to 0, then that means 0 has to be either x plus 2, or e to the x. If x is 0, then that would result in a critical value. If x is -2, that would result in a critical value. And if 0 equals e to the x, well, that can't happen. So the only two critical values we get are when x is 0 and when x is -2. Let's look at the critical points, the corresponding critical points. When you plug in 0 into your original function, you get an output which is 0. When you plug in -2 into the original function, you get an output which is -2 squared, that's 4, times e to the -2 power. Now that 4 times e to the -2 power, that's hard to graph. So I'm going to just call that a decimal of 0.54. So -2 comma 0.54. And I'll move on from that. Let's take a look, now that I've found my critical values, let's try to figure out what would happen if I took the second derivative. I'll look for critical points and then look for concavity at certain places. Second derivative, I'm going to have to use a product rule once again. First component, second component. First component, take the derivative of. So 2x plus 2 times my normal second component plus normal first component multiplied times the derivative of the second component. Derivative of the second component is once again e to the x. I can combine like terms. Notice that both of these have e to the x out and back, so I can combine the polynomials inside and find out that my second derivative is x squared plus 4x plus 2 multiplied times e to the x power. If I'm looking for points of inflection, I set my second derivative equal to 0. X squared plus 4x plus 2 times e to the x is now set equal to 0. The only time this can be equal to 0 is when x squared plus 4x plus 2 is 0, because e to the x can never be equal to 0. You might say, well, this can't be factored, and that's right, this can't be factored. However, the solutions to this are, in fact, real numbers. You can either use the quadratic formula, or completing the square, or graphing to figure out that the solution to this is -2 plus or minus the square root of 2. So -2 plus root 2 is one solution. -2 minus root 2 is another solution. Again, just use the quadratic formula and simplify it, and you'll get that. That means we have 2 inflection points. I don't like writing square root of 2 right now at this stage. So instead, what I'm going to do is I'm going to approximate this. If I take -2 plus square root of 2, I end up with about a -0.59. And if I do -2 minus square root of 2, I end up with about a -3.41. If I plug in -0.59 into my original function, remember my original function was x squared times e to the x, I get an output value of -0.59 squared times e to the -0.59. That's an output value of approximately 0.19. When I do the same thing with -3.41, -3.41 squared multiplied times e to the -3.41, I end up with an output value of 0.38. Here are my 2 points of inflection. Since I have the second derivative here, I might as well look at the concavity at my critical points. Let's do concavity when x is equal to 0. When x is equal to 0, I plug in 0 into my second derivative. I end up with 2 times e to the 0, which is positive. The only thing I care about is that it's positive. I know my function is concave up at the critical point 0, 0. At the critical value of -2, if I plug that in to my second derivative, -2 squared plus 4 times -2 plus 2, that's -2 times e to the -2. The only thing that really matters is that it's negative, but it's about -0.27. We're concave down there. So we see that we're concave up at this critical point. By the way, concave up, remember, at a critical point, that means we're at a relative minimum. And concave down at a critical point means we're at a relative maximum. So I know we get a relative minimum at 0, 0. We get a relative maximum at -2.54. We have these inflection points where we change concavity. And we know it changes concavity because you can go in between these. We've already done so at -2 and at +0. So we know where we're concave up, concave down. The only really thing I need to figure out is the behavior of the function as x goes to positive and negative infinity. Well, technically, we only care about negative infinity because we know that beyond -3.14, beyond the x value of -3.14, we know we're concave up. So we know we're going to be pointing up. So we can deduce from that that as x goes to positive infinity, since we're going concave up, the function is going to be traveling towards positive infinity as well. You can also determine that by just saying what's going to happen when you plug in bigger and bigger values into the polynomial and when you plug in bigger and bigger values into your exponent. In both cases, they're growing. And if two things are growing and we're multiplying them, then they're getting bigger. This is a little bit harder to see as x goes to negative infinity, because we think about this function, if I plug in negative infinity, then you get negative infinity squared. That's going to become a really, really big positive number. But e to the negative infinity is going to become a number that's really, really close to 0. In fact, one way you can think of this is that we're getting sort of like infinity squared divided by e to the infinity. And so which one of those is going to grow faster? It's kind of a competition between a polynomial and an exponential as x goes out towards infinity, or in this case, x goes out to negative infinity. So the competition, it turns out, is always one. The faster growth is by the exponential piece. The exponential piece grows faster, and therefore the denominator is getting a lot bigger than the numerator. The denominator is getting bigger. That means this fraction is going towards 0. Therefore, as x gets closer to negative infinity, my function's behavior gets closer towards 0. Now we have all of the components we need to sketch the curve of this graph. I don't know what scale on this graph is going to be the best, so let me just start plotting some points. We have two critical points. One of them is the point 0, 0, that's the origin. The other is the point approximately -2, 0.54. I have 2 points of inflection, one of which is -0.59, 0.19, or at least approximately that. And the other is -3.41, 0.38. So here's my points. Let me just color these. Let's color the critical points in black and color the points of inflection in blue. That's what we'll do. I know my graph goes through the critical points and through the points of inflection. I also know that in between these points of inflection, specifically at -2, my graph is concave down. So I know that we're going to be concave down. We're going to look like a parabola pointing down there. Then, to the right of this point of inflection, to the right of the 0.59, 0.19, it's going to start doing concave up. So we're going to do concave up and then go off to infinity. So it's going to look something like that. Up, concave up, then concave down. And then to the left, we approach 0. Now, I didn't actually determine this, but if you would have plugged in a point like -4, you would have seen that your second derivative would have been negative. So we're concave down. Did I say negative? See, your second derivative is positive, so you're concave up again. So from here to the left, we're concave up, but we're approaching 0 there. So my graph should look something similar to this. Let's see if y equals x squared multiplied times e to the x looks similar. Yeah, I didn't draw it as well as I should have, but you can see what's going on. Let's take and eliminate my drawing here. You can see how that works. I had the general gist right. Again, off to the right, it grew a lot steeper than I had drawn it, but I had this pretty much exactly the same. So there you go. That's a sketch of this curve. That's an interesting graph right there.